Good day. I'm Norman Wildberger. This is one of a series of foundational videos on mathematics where we're attempting to lay out new and more careful foundations for the subject. But together with building up the subject, we also need to critique current practice when it needs critiquing. And when it comes to angles, mathematics is sorely in need of some severe critiquing. The usual concept runs something like this. We have two rays, say R1 and R2, and an angle is supposedly a quantity which measures the separation between these two rays. It's presented to young people as a very elementary, simple, easy to work with concept, when the reality is that it's far from being any of those. It's a difficult concept, it's actually hard to work with, and it leads to a lot of logical weakness and insecurity in geometry and trigonometry. The difficulty you can see by opening some geometry and trigonometry books and see how many of them actually have a careful and precise definition of the concept of an angle. Almost none of them do. We're going to talk about some basic issues. We're going to talk about problems with the definitions, some historical remarks. We're going to talk about units and the irrationality that's involved in the concept, the ambiguities and the imprecisions that angles bring to many practical problems, and how the concept forces young people to rely on transcendental functions, which are in fact quite irrelevant for doing geometry and trigonometry. So let's have a look, to start with, at what exactly is an angle. Students in primary school are introduced to an angle in the same way that the Babylonians 4,000 years ago used the concept. We take a circle and we divide it into 360 equal pieces, and we call each one of those pieces a degree. So here's my handwritten attempt at doing that. So there's 90, that's 1/4 of the way along, and then I've divided 90 as best as I could into three pieces, call them 60 and 30, and then I've sort of by hand subdivided each of those into three pieces so that each one of these little arcs is 10 degrees. And I haven't bothered further trying to subdivide them. Doing this approximately is not hard, but doing it accurately poses grave difficulties. In fact, in some sense, it's really impossible. This goes back to the ancient Greeks, who struggled with the idea of how to trisect an angle. So if we have just that circular piece from 30 to 60, and we want to divide it up into three equal arcs, it's very difficult to do this. And in fact, 2,000 years after the Greeks struggled with it, it was finally proven that you couldn't do this with ruler and compass. The situation is dramatically different for line segments, where this construction that we've seen before, you create three equal segments there, and then you draw parallel lines, and that splits any line segment into three equal pieces. There's no parallel result for arcs of circles. So that when we say divide the circle into 360 equal pieces, it's easy to say, but it's actually hard to do. A three-dimensional implementation of this is quite difficult. If you actually have a concrete situation, you want to measure some angles between beams, it's not clear how you can get your protractor up there. The additivity that seems to be built into the situation is largely illusory. If you have two angles which are bigger, say like that one 254 degrees, if we add that angle to itself, then we're not going to get 508, but we're going to rather have to subtract 360 to get the angle in the right range. But the most natural problem is that it's really a physical answer relying on a piece of an instrument, a protractor. It's not really a precise mathematical definition. There's a variant to this scheme that's a little bit more constructive, that uses bisections only. So the idea is to divide the circle not into 360 pieces, but into first two pieces, and then into four pieces, and then to continuously divide each arc into two equal arcs. That can be done relatively easily because, for example, to divide that arc into two just requires taking that chord and finding its midpoint. So that will automatically split that arc into two equal ones. So then we can further subdivide this arc into 2 equal pieces, and then this one into 2 equal pieces, and so on. That gives us a way of pinning down a lot of angles precisely, but unfortunately most of the angles that actually occur in practice are not obtainable in a finite number of steps with this kind of bisection. So what it requires is a binary approach or an approximation approach to creating angles by an infinite sequence of such bisections. For this reason, this approach is not too often used. There are also some number theoretical difficulties with it that we won't talk about. So here now is the modern definition that students learn in high school after they've already spent a few years becoming familiar with the Babylonian 360-degree definition. They learn a new way of thinking about an angle. Here are 2 rays. We construct a circle of some radius r centered at the intersection point. And then we define the angle as a ratio of 2 lengths. The length of the arc of the circle divided by this length, the radius of the circle. L divided by r is now our definition of theta. Now that's going to be a different kind of angle than the Babylonian angle because, for example, in a situation like this length here is maybe a little bit more than the radius, maybe 1.2 times the radius, say. That'll mean that this angle here will actually have the value 1.2, roughly, because the ratio of this length to this length is roughly 1.2. So in the Babylonian system would be maybe 70 degrees, quite different from 1.2. All right, what's the problem with this definition? This definition is a big cheat, okay, in 2 very important ways. First of all, it really needs a prior theory of arc length. You need to understand what the definition of this arc length is and have some effective means of computing it. This is a point that Archimedes well understood. He spent a lot of time and thought trying to compute the arc length of a portion of a circle in his attempt to find pi accurately. And what he did is he used a succession of interior and exterior polygons, and he approximated this length better and better by increasing the number of sides to these approximating polygons. It was quite a tour de force. And Archimedes really anticipated calculus when he was doing this kind of limiting procedure. Calculus is really necessary for any kind of coherent theory of arc length. The other serious difficulty with this definition is that it requires a prior theory of Euclidean geometry first. Because there's a theorem behind here, which is that if you say double the radius of this circle, then the length of the circular arc will also double. That's not entirely obvious. In fact, it's not true on the surface of a sphere or on some other curved surface. That theorem requires a proof, and to prove that you first need a theory of Euclidean geometry, or you need to have developed some calculus. Either way, this definition as it stands rests on assumptions and work that has not been done by the high school students who meet it. And even at the university level, the subsequent basis has not been established when people are using this definition of angle. So it's a cheat. And this cheat has many ramifications throughout modern mathematics. Next time we're going to talk more about the problems with angles. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.